Hello, and welcome to the next video in my series on finite mathematics. Now I do want to say, if you're watching this video because you're having problems in your finite math class, I want you to stay positive and keep your chin up. If you're watching this video, it means you've come pretty far in your education up to this point. So I know with a little bit of hard work, patience, and practice, you can get through it. I have faith in you, and so should you. Now also, these videos are geared towards individuals who are relatively new to finite math, so I will just be going over the very basics in great detail. I will be working through the examples very slowly, very deliberately, and explaining every single step that we do so you have a very firm, comprehensive grasp of what we're talking about. So let's go ahead and dive into this video's topic. Now in this video, we're going to be talking about Markov chains. So this is a topic that comes up in finite math courses, and it's probably one of the ones that gives students the most headache because it takes probability from the first part of the course and matrix operations from the middle part and then smashes them together into Markov chains or Markov processes. So we're going to talk about what they are, and then we're going to talk about how to set up transition matrices and how to set up transition diagrams based on the wording of the problem. So let's go ahead and get started with an example. So the first example we're going to look at has to do with auto insurance risk, and it's a very simple problem that will get us started in how to understand Markov chains. So an automobile insurance company places its policyholders into one of two categories when the policy renews. They either go into the low risk category or the high risk category. Now a motorist is high risk if the policyholder has received a moving violation or a ticket within the past 12 months, and low risk if they've had 0 tickets in the past 12 months. So when the policy renews, the insurance company will look back over the past 12 months. If that person has a ticket, they will get put in the high risk group. If that person does not have a ticket, they will get put in the low risk group. It's pretty much that straightforward. Now at any given moment, a motorist is in one of the two categories, or states. We call these states. They're either in the low risk state or the high risk state. And of course, this only happens when the policy renews. So I could be in the high risk category right now, and my auto policy renews, but in the past 12 months, I have not had a speeding ticket or anything like that. So when my policy renews, I will be placed in the low risk group. So this is sort of a process. Depending on what has happened in the past 12 months, you can go from low risk to high risk, back to low risk, etc., simply based on your driving record. Okay, so just one of two categories are what we call states. Now, based on company data, a motorist that is currently high risk has a 60% chance of being denoted high risk again when their policy renews, and a 40% chance of being moved to low risk. So, let's say a motorist right now is high risk. When their policy renews, there's a 60% chance they remain high risk, or a 40% chance they go into the low risk group. If you notice, those percentages add up to 100. They have to go into one of the two groups. Now, a low-risk driver, on the other hand, has a 15% chance of moving to the high-risk category and an 85% chance of remaining low-risk. So a low-risk driver right now, when their policy renews, they have a 15% chance of moving to high-risk and an 85% chance of remaining in the low-risk state or the low-risk category. So notice again, those add up to 100%. So here is our task for this problem. We're going to set up a probability tree, a transition diagram, and a transition matrix for this process. And again, this is a very simple example that will get you started towards a better understanding of Markov chains. So let's talk about what a state is. A state is simply the category, for this problem at least, a motorist can be in at any given time. So another way of thinking of a state is a category or some characteristic or something like that. It just depends on the problem. And this problem is sort of a category. Now each driver is either in the high-risk state or the low-risk state. Every driver is in a state and no drivers are in both states. So every driver has to be either high risk or low risk based on their previous 12 months driving behavior. And of course, a driver cannot be in both states. They're mutually exclusive. Now, drivers can move between states or return to the same state when their policy is renewed. So if they're at high risk now, they could be high risk when it renews or move to low risk. If they're low risk now, they could move to high risk or remain in low risk. So they're going to move to some other state when it renews, whether it's the same one or a different one. Now, an important note here, this information only tells us the probability of moving from state to state. In this case, it's from moving category to category when the policy renews. So it's about the transitioning. It really doesn't tell us right now anything about the probability of starting in either state. So we don't know, at least right now, what the probability of being high state or low state is right this second. We just know when the policy comes up that we have probabilities of where they're going to go from here. Now, there are problems that we're going to do in a later video where we do know the probability of being high risk or low risk or whatever right now. But we're just focusing on the transition diagrams, the transition matrices. So we're looking at just the movement from state to state to state to state over several processes. In this case, several renewals over time. Okay, so what are Markov chains officially? Basically, they're a combination of probabilities and matrix operations. So again, you learn a lot of probability usually in the first part of finite math, and then somewhere towards the middle or 2/3 mark, you learn about matrix operations. And then Markov chains take those two things and combine them into sort of a model that allows you to do more complex type problems. So they model a process that proceeds in steps. So steps in time or some sort of sequence or trials, over a period of steps. And it's basically what we're doing here. It's a series of probability trees. But with a Markov chain, we can do a process or a series of probability trees, that are way numerous. So that's a technical term, way numerous. But we could do 5, 10, 30 different steps into the future. Now, if you want to do a probability tree that has 13 branches on it, or 30 branches on it, go right ahead. So this keeps us from having to do that. And you'll see what I mean by that as we go. The model can be in one state at each step. When the next step occurs, the process can be in the same state or move to another state. Movements between states are defined by probabilities. And remember from our problem, we gave you those. And we can then find the probability of being in any given state many steps into the process. And this is the really important part and the power of Markov chains. So for example, I've been with my current auto insurance company for 10 years. Now, based on this model, if my insurance company did this model, which I don't think they do, we could find out what is my probability of being either high risk or low risk 10 years from now. It's pretty cool, huh? So we can do things far into the future using Markov chains and the matrix operations that go with them. So there are some really good, solid, practical problems where Markov chains are used, and we'll talk about those as we do more problems. So they're very, very handy for finding out things far into the future that would be impractical. We couldn't do a 10-year probability tree. Well, we could. It might take this out of a wall, though, to write it all out. Okay, so it's back to our problem here. Now we're talking about where we're going from to where we're going to. So let's say we start in the high risk state. Where can we go? Where can we go to as far as states go? Well, we could go to the high risk state when our policy renews, or we could go to the low risk state when our policy renews. Again, that just depends on our driving habits over the past 12 months. Now remember, the probability of going from high risk and being renewed and going back into high risk is 0.6 or 60%. The probability of being in high risk, having your policy renew, and then going into low risk is 0.4. So this is a very basic, very simple probability tree. If you're doing this at the end of a finite math course, then you've had these type of probability trees before. So this is going from high risk state, then either to high risk or low risk, and then the probabilities that go with each. Or we can start in low risk. Then of course we can go from low risk to high risk, or low risk to low risk. Then of course those have probabilities. So remember, the probability of going from low risk to high risk when your policy renews is 0.15, and the probability of remaining low risk is 0.85. So let's put these together. So we start in high risk. We can go either to high risk or low risk. Then we have the probability of 0.6 and 0.4. Notice that those probabilities add up to 1. Or we can be in low risk right now. That means we can move to high risk, or we can move to low risk. And those probabilities are 0.15 and 0.85. So look at this picture right here. It's one of the most important pictures you'll see with respect to understanding Markov chains. All we're doing is moving from state to state over a series of steps. So we can think of, on the left-hand side is where we are now, and then on the right-hand side it's where we could be when our policy renews every 6 months or a year or whatever it might be. And since there are two states, we can go from state to state with a certain probability. It's just two probability trees. It's very straightforward, very simple stuff. Now, of course, we're going to put it in a more complex form as we go, but at its heart, this is basically what it is, okay? So if you need to, pause this video right here, take a look at this diagram, because this really is the heart of what we're getting at in Markov chains. Okay, let's go ahead and continue. Now, we just did a couple of probability trees, but in Markov chains, we draw transition diagrams. It's this different way of representing the exact same information, okay? So, on one node, we have our high risk, and on the other one, we have our low risk. Those are our two states we could be in. Now we're going from a state to another state. Just a reminder that going from high risk to high risk is 0.6, high risk to low risk is 0.4, and then low risk to high risk is 0.15, low risk to low risk is 0.85. Now we do some arrows to show how we could proceed through this process. So, if we start in state 1, our policy renews, and we're high risk again, we go right back into that state. So we go from high risk to high risk. And of course that probability is 0.6. Now, if we're in high risk now, we could go to low risk if we've been a good driver. Now the probability of that is 0.4. Now notice here a few things. That the probabilities add up to 1, so every arrow coming out of a state has to add up to 1. So 0.6 and 0.4 add up to 1. And of course you can go from state 1 to state 1, or you can go from state 1 to state 2. Now for state 2, if we're starting here, we can go back in the low risk. That's a probability of 0.85. Or we can be moved in the high risk category, which is a probability of 0.15. And congratulations, you just did your first transition diagram. This is it. So, think about the power of how we could use these. Let's say you were with your insurance company for 5 years or 5 renewal periods, whatever it might be. And you come in and they say, okay, you're a good driver. You're going to start in low risk. So that's where you kind of start. And then the next renewal comes up and you've been a good driver, so you stay in low risk. And then maybe something happens the next year and then you get a ticket. So you're moved into high risk. So now we've gone 2 years into the future. You started in low, then you went to low, and then you went to high. Now let's say you had a clean driving record again, then you went back to low. Then maybe you had another ticket and you went back to high. So that would cover your 5 renewals. So you can sort of picture how we would go through this diagram. And if I grab the marker here, we can actually show that. So if we started here in low risk, right here. Now let's say in the next year, you're also low risk again. So we come back here, like that. But then you get a ticket. So the next time, you go over to high risk, right here. But then the next year, you're good. So you go back to low risk, here. And let's say you're low risk again. So the next renewal, you come back to low risk. And then you have a ticket again, unfortunately, and you go back into high risk. So that is 5 renewal periods, 5 years into the future. So we went from, started in low, we went from low to low, low to high, high to low, low to low, and low to high. And to figure out the probability of doing that, all we'd have to do is multiply together all the probabilities in that process. That's it. And again, we're going to do that in future problems. So the power of Markov chains allow us to take these things far into the future, many, many steps. And in this case, it's years. Okay? So let me see if I can clear that. There we go. Let's go ahead and continue. Now we can also write this as a matrix. So I just want to tell you here, the 2 probability trees we did at the beginning, the transition diagram we just did, and the transition matrix we're going to do, it's different ways of representing the exact same information. So just a reminder, here are our probabilities for high to high, high to low, low to high, and low to low. Now we set this up as a matrix. On the left-hand side, we have where we're starting from, and then on the top is where we're going to. So the probability of going high to high would be in the top left corner of our matrix. The probability of going from high to low would be in the top right, and then so on and so forth. So if we transfer these probabilities to a transition matrix, it would look like this. So you can see the probability of going from high to high risk is 0.6. Probability of going from high risk to low risk is 0.4. Notice that row adds up to 1. Then the probability of going from low risk to high risk is 0.15. And the probability of going from low risk to low risk is 0.85. Exact same information, it's just represented in a different way, because we have to have it in this way to do more complex problems involving Markov chains. So again, notice that each row sums up to 1. All right, let's do one more example, and then we'll be done with the introduction, at least, to Markov chains. And this one has to do with basketball free throws, or foul shots. So in certain foul situations, a basketball player is entitled to 2 free throw shots, 2 foul shots. Now a coach with the team analyzes the team data and learns that if the player makes the first shot, he or she is twice as likely to make the second shot as they are to miss. Okay, so let's think about that. If the player shoots the ball and makes the first foul shot, they are twice as likely to make the second one as they are to miss it. Now notice there are no numerical probabilities in here. There are relative probabilities. So we're going to have to figure out the numbers here in a minute. Now if the player misses the first shot, he or she is 3 times as likely to miss the second shot as to make it. So if the player shoots the ball and bricks it off the rim, then the player is 3 times as likely to miss the second shot as they are to make it. So again, at least in real world terms, it's this idea of confidence. So if you make the first shot, you feel like you can do it, so you have a better chance of making the second one. On the flip side, if you miss the first shot, it kind of gets in your head a bit, and you're 3 times as likely to miss the next shot as you are to make it. But again, there are no probabilities actually in the text. We're going to have to figure out what those are. So again, we're going to draw a probability tree, transition diagram, and transition matrix for this problem. So where are we going from and to? Well, let's say we make the first shot. So we'll call state 1 is a make. What can happen the second time? Where are we going to? Well, we can make the second shot, or the player can miss the second shot. So we're changing states. Now notice, all it says is 2 times as likely to miss, or 2 times as likely to make than miss. So we write that this way: 2x and x. So 2 times as likely to make as to miss. So 2x and x. Now remember, what do those have to add up to? They have to add up to 1. So we can set up a simple little algebra problem here. 2x plus x has to equal 1. So that's 3x equals 1. So x equals 1/3. Simple algebra problem. But now we have to go back and substitute that back into the problem. So if x is 1/3, then the probabilities are 2/3 and 1/3. 2 times as likely to make as to miss. So those are our 2 states that we can go from and then to, and the probability associated with each state. Now we could also miss the first shot. So if we miss the first shot, we could make the second one or miss the second one. Now it said 3 times as likely to miss the second as to make it. If you miss the first time, I guess it kind of gets in your head and you lose your confidence. So 3 times as likely to miss as to make. So we say 3x and x. Now remember, those have to add up to 1. So using algebra again, x plus 3x equals 1. So 4x equals 1. X equals 1/4. So we substitute x back in, and our probabilities are 1/4 and 3/4. So if we miss the first shot, we have a 25% chance of making the next one. If we miss the first shot, we have a 75% chance of also missing the second one. So let's go ahead and do a transition diagram. So our state 1 is make, state 2 is miss. So that's just a reminder of our probabilities there as they're stated in the problem. So if we make the first shot and then we make the second one, remember that was 2x, make the first one, miss the second one, that's x, because we're 2 times as likely to make the second one as to miss if we made the first shot. Now if we miss our first shot, we're 3 times as likely to miss again on the second one as to make. So all I did was write in the relative probabilities into our transition diagram. That's all I did. Now luckily for us, we already went ahead and figured out the probabilities. So if we just substitute those back in, our transition diagram looks like this. So state 1 to state 1, or make to make, is 2/3. Make to miss is 1/3. If we miss, then our miss to miss is 3/4, and miss to make is 1/4. So this should be making a fair amount of sense right now. It's actually pretty straightforward. You just have to do a couple of examples to get the flow and see how they're set up. So how about our transition matrix? So there are probabilities, just as a reminder. Now if we go ahead and put in our relative probabilities from the problem, remember make to make is 2 times as likely as to miss, so we have 2x and x in the top row. If we miss the first shot, then we're 3 times as likely to miss the second one as well, so that's 3x and x. Same thing we had in the trees, same thing we had in the diagram. So if we go ahead and put that into our matrix, it looks like this. So we have 2/3 and 1/3 on the top. Of course, that adds up to 1. And on the bottom, we have 1/4 and 3/4. That also adds up to 1. Again, same information, just represented in a different way. Okay, let's review and then we're done. So, just remember that Markov chains are just a combination of probabilities and matrix operations. So, there you saw that we use our probabilities to do our trees, we use our probabilities to do our transition diagrams, and then basically, to do the transition matrix, we just sort of moved the probabilities into a matrix form. They model a process that proceeds in steps. So time or sequence or trials. So you can sort of think of our basketball shots as 2 trials. So the player shoots the first shot, they make or miss, and then they take the second shot and make or miss. In terms of our auto insurance, we can think of that as time. So you're placed in a category when you first sign up for your insurance. When it renews, you are put into the same or different risk category. And then the next time you renew, you're put in the same or different. Next time you renew, same or different, etc. So it's a process over time. The model can be in one state at each step. In these problems, we had 2 states. So in the auto insurance, we had high risk and low risk. In the basketball shots, we had make and miss. But they could be anything. They could be whether or not a customer uses ketchup A or ketchup B. That's a common one. That's a common Markov chain problem that's used in marketing type situations. We could do whether or not a student graduated or not from school or something like that. So they could have 2 states, graduate, not graduate. So you can see a state can just be any sort of category or characteristic, as long as they're mutually exclusive and a person or whatever can only be in one or the other. When the next step occurs, the process can be in the same state or move to another state. So in our insurance example, if we're high risk now, we could be high risk next time or low risk, depending on our driving behavior the year before. In the basketball situation, if we miss the first shot, we could miss the second one or make it. So we would go on to a different state. Now, movements between states are defined by probabilities. And I think we've gone over that pretty well in these 2 examples. Just remember the probabilities out of a state into the next, step have to equal 1. Now, the power of Markov chains is being able to take these, sequences or time steps or trials many steps into the future. So, for the car insurance example, we could figure out the probability of being high or low risk 15 years into the future. For the basketball example, we could figure out, over the course of a season, how many makes or misses we expect in situations where our players take 2 foul shots. We could do that with probability trees, but they would be the size of a small wall. So these allow us to do that, and in future videos I'll show you how that works. Okay, well, we are done with our introduction to Markov chains. I know this was a lot, but I wanted to give you several very concrete examples that you could repeat in your work or follow along with, step by step. So just a reminder, if you're watching this video because you're having problems in the course, I want you to stay positive and keep your head up. You've come this far, and I know with some hard work and patience, you can do well. And again, I have faith in you, and so should you. So all that being said, thank you very much for watching, and I look forward to seeing you again next time.